This is the fourth video lecture on the course Computational Hydraulics. Last class we were talking about the derivation of Saint-Venant's equation. And we have tried to put Saint-Venant equation to describe flow at any point and any time by using two variables. It may either be explained by using Q and A, in which case you would have the conservation form of the Saint-Venant equation, or you may use velocity and flow depth, in which case you do have the non-conservation form of the Saint-Venant equation. So since two variables are required to describe the flow at any point and any time, we need to have two sets of equations, one on continuity and the other one on momentum. Sometimes we also describe the non-conservation form of the equation, the primitive form or Eulerian form of the equation. And we have tried to show that the simplest form of the Saint-Venant equation would result in a kinematic wave equation, in which case the bottom slope would have the same magnitude as the friction slope. If we add the pressure term, then it would end up with the diffusion wave. And if we include the whole of the terms, including the inertia terms, both local acceleration and convective acceleration, then we would have the full dynamic wave equation, which is typically used for unsteady flow mainly. Now, to solve the Saint-Venant equation, we commonly use a number of procedures, but among others, we use finite difference method. We may use finite element method or finite volume method, or you may use method of characteristics. So in the next couple of chapters, we'll be talking about, among others, on the method of characteristics first, and then we'll move on to the finite difference method. Now, method of characteristics. Method of characteristics is basically a graphical techniques that attempts to solve partial differential equations. It would simplify to ordinary differential equations. As you know, ordinary differential equations, they are differential equations that involve only one independent variable, whereas partial differential equations would involve a number of independent variables. Now, here we are going to use the non-conservation form of the continuity and momentum equations. So they are expressed in terms of the H and V, basically. And we know earlier we have been talking about the celerity, remember? So celerity, we have said, basically it's a critical velocity. When there is a disturbance in shallow water in open channels, then this disturbance will propagate in both directions with the magnitude of square root of acceleration due to gravity times the depth of flow. So for rectangular channels, this would mean C is equal to radical of G times H. Now, for an observer standing on the bank of a river, then the absolute speed of the small wave would be aided by flow of water. So the absolute speed of the wave would be, in the downstream direction, it would be the velocity of flow plus the celerity. Whereas in upstream direction, it would be against the flow direction, so it would be V minus celerity. So this is the absolute speed of the small wave. Mind you, this is the case under static water or still water, where there is no this is a very general equation. So the C with the celerity under static conditions, so V plus C and V minus C. If the velocity is very much small, then definitely the wave may have a chance to move upstream, which is very typical in subcritical flows. I remember we were talking about here the different possibilities for the travel of the disturbance in case of subcritical flows, and in case of still water, the disturbance will propagate in both directions. Whereas in case of still water, it would be constant in both directions. Whereas in case of subcritical flow, it would mainly be a large amount of disturbance will propagate downstream in the direction of flow, and a smaller magnitude would flow upstream, which is V minus C. But at some point, as the speed of the water keeps on increasing, and it becomes equal to the celerity, it would be equal to celerity typically during critical flows. So C would be equal to V, in which case the upstream propagation of the wave will culminate. And as the speed keeps on increasing, the velocity of water keeps on increasing, then the flow regime would traverse to the supercritical flow, in which the velocity is much higher than the celerity. There would only be downstream propagation of the wave, in which case it would be only C plus V. Now, if we try to differentiate this celerity with respect to C square, with respect to time, and with respect to space, you can obtain from calculus 2C times partial derivative of C with respect to T. And this, as you know, we have already said for rectangular channels, C is equal to radical of GH. So from here, you can obtain this is approximately equal to G times partial derivative of H with respect to time, basically, since G is constant. Similarly, if you partially differentiate C squared with respect to X, then you'd obtain 2 times the celerity, partial derivative of celerity with respect to X, which is approximately equal to G times partial derivative of the flow depth with respect to X. Now, if you try to multiply in the earlier equation, in equation 4.1 and 4.2, first, if you multiply equation 4.1 by G throughout, mind you, in this set of equations, A over B would tell you A is the cross-sectional area and B is the top width. So A over B would indicate the hydraulic depth. So if you multiply by G, you can clearly see that G times partial derivative of H with respect to T is the term which we have obtained in equation 4.3. So it would be replaced by 2C partial derivative of C at T. And then hydraulic depth times G is basically C squared, because C is equal to radical of GH, and times partial derivative of V with respect to X plus G times V times partial derivative of H with respect to X. G times partial derivative of H with respect to X, we have shown in equation 4.4 is 2C partial derivative of C with respect to X. Now, if you just divide the whole term then by C, then you would obtain the equation 4.5. Similarly, if you try to replace in equation 4.2 the term g times partial derivative of h with respect to x by 2c partial derivative of c with respect to x, then you obtain equation 4.6. Now, using these two sets of equations, if you add equation 4.5 and equation 4.6, then you would obtain this equation, which is equation 4.7. If you deduct equation 4.6 from equation 4.5, then you would obtain equation 4.8 here. Now remember, when we talked about total derivatives, if the variable v varies in space and time, or the variable y varies in space and time, then the total derivative is given as dv per dt, change in velocity per change in time. Total derivative, it is the change in v as v is traveling in a moving fluid. Changing, if v is velocity, for example, this is change in velocity while the observer is moving. Is change in velocity with time plus change in x per change in time, that is the speed of the observer, times change in velocity per change in cross section. Which would physically mean the change in this total derivative would tell you the change in velocity for the change in velocity for a moving observer, you can say, essentially. So that moving observer that's moving with the same speed with the flow of water would only detect the change in velocity with respect to time, basically. Now, this equation, either equation 4.9 and equation 4.10, could easily be related with equation 4.7 and equation 4.8. If you take the last term in equation 4.7 and equation 4.8 to the other side, then the two equations are similar structure. This would mean here we are trying to, instead of the v or the y in the total derivative term here, we are trying to differentiate or finding the derivatives, total derivatives of v plus 2c or v minus 2c. So total derivatives of v plus 2c per dt as per this set of representation is going to be represented by negative g sf minus s naught. Now you can see the similarity between the two. So the first term, which is the partial derivative of v plus 2c with respect to t, is similar with change in partial derivative of v with t, essentially. And the constant term, which is v plus c, would indicate dx per dt in equation 4.7. v plus c would indicate in equation 4.9 dx per dt. And the partial derivative of v plus 2c with respect to x would indicate partial derivative in equation 4.9, partial derivative of v with respect to x, basically. By the same token, you can easily see partial derivative of total derivative of v minus 2c with respect to t is negative g friction slope minus bed slope. Now, these two equations would form these trajectories would form characteristics along a certain respective characteristics trajectories. Essentially, the wave is traversing along dx per dt with the slope of of course, the inverse essentially, with slope of dt per dx, which is 1 over v plus c, you are going to have a forward characteristics that would propagate an information. So along that line, along the line of v plus c, information would, on the fluid property, would propagate along that direction. So there are two pairs of characteristics directions. The forward characteristics, typically labeled as C plus. The backward characteristics, which is typically labeled as C minus. So you can see the total derivative d v plus 2c dt. This would propagate along the line dx per dt, which is along the line v plus c, along the forward characteristics, whereas total derivative of v minus 2c dt, that would propagate along the characteristics direction of v minus c, or along the backward characteristics of c minus. So essentially, we have now 4 system of characteristics equations. So that will replace the differential form of the Saint-Venant equation. So from now on, we no more talk about the Saint-Venant equation as it's commonly expressed, but we would employ these equations from 4.11 to 4.14 to describe those system of equations. Now, as you can see here, the families of the forward characteristics and backward characteristics, C plus and C minus, information would propagate along those lines. So in terms of space and time, if we try to look at the flow properties along the forward characteristics with a slope of essentially 1 over v plus c, because t is in the y direction and the x is in the x direction, so I'm just inverting that. So the slope is 1 over v plus c for the forward characteristics. For the backward characteristics, or for c minus, the characteristics direction, the slope is 1 over v minus c. So you can see here, in case of, this is very much true in case of subcritical flow. Remember, earlier we have said that here, we have said that a small disturbance in shallow water in an open channel would traverse in static water in both directions with a speed of c, which we typically call the celerity. Here, the velocity of flow is 0. But when there is a small velocity that's not higher than the celerity, then the wave would traverse not only in the downstream direction, but it would also traverse in the upstream direction with a velocity of v minus c. And the absolute wave velocity in the downstream direction is going to be v plus c, basically. So in a subcritical flow, the wave would propagate in both directions. One upstream, the other one downstream. So flow characteristics at a point would be affected from both sides, from upstream and from downstream in case of subcritical flow. In case of critical flow and supercritical flow, the wave will advance only in one direction, downstream. Whereas in critical flow, the absolute wave velocity is basically the same as the velocity of water. So the absolute, the velocity of water is the same as the celerity. So the absolute wave velocity is going to be twice of the celerity. Whereas in case of supercritical flow, the velocity of water exceeds the celerity. So the absolute wave velocity is v plus c, basically. Now you can see here, in case of subcritical flow, from the figure you can see at a given point, the characteristic flow directions, both from upstream and downstream, would influence at a given point. But in case of supercritical flow, since the wave is traversing only downstream, at a given point where those two characteristic lines are merging, the possibility for a wave from downstream to influence an upstream point in a flow which is propagating downstream is nil. Basically, in case of supercritical flow, both of the pair of the backward and forward characteristics are positive. They are in the same direction, actually. Whereas in case of subcritical flow, they are in opposite directions. Now, if we assume for a horizontal frictionless channel in the characteristic system of equations, now we are trying to substitute instead of G S0 minus S5 here in this set of equations. If we assume the horizontal, which means S0 is 0, frictionless, in which case SF is 0. So since SF and S0 are equal, which is to mean in kinematic wave routing, when S0 and SF are equal, so this term is going to be 0. So as you can see, the total derivative dv plus 2c per dt, or total derivative of v minus 2c dt are going to be 0 in that case. Then we are going to have v plus 2c is going to be constant, and v minus 2c is going to be also constant. So we express v plus 2c as j plus and v minus 2c as j minus, and we call these constants Riemann invariants. So for the horizontal frictionless channel, assuming straight characteristics directions, as you can see in plot fig 4.2, at a given point, P, C plus, along the C plus characteristics and along C minus characteristics, they meet at point P. And the values of the Riemann invariance along the C plus direction is constant. Along the C minus direction is going to be constant. Along the C plus direction characteristics is going to be V plus 2C. Along C minus characteristics is going to be V minus 2C. And as you know from the characteristics directions, which we have tried to derive earlier, is going to be V plus C for the forward characteristics and V minus C for the backward characteristics. And C, remember, is for rectangular channels, is going to be radical of GH. So the x per dt is going to be V plus radical of GH, or for the forward characteristics, and for the backward characteristics is going to be the x per dt is equal to V minus radical of GH. Now, we have to be careful when we use this Riemann invariance. If we introduce additional terms like lateral flow, bottom slope, and bottom friction, this Riemann invariance will contain correction terms and will no longer be invariant, which means in the earlier derivation of the Saint-Venant equation, if you do have lateral inflow like Q, or if SF, and if there is a friction slope, and if there is bed slope, then obviously SF minus S naught will no longer be 0. So under such circumstance, then we cannot talk about the Riemann invariance, actually. Now, as you have seen earlier, in case of still water, now the characteristics directions, in case of still water, at a given intersection point, from both downstream and upstream, the value of C is going to be constant. So the at point P, the influence from, there would be influence from upstream and downstream for still water. So in figure 4.3, that's the case for still water. So the shaded area would show you the region of dependence. So the flow characteristics at P would depend on the shaded area, both in the figure A, B, and C. As you can see, in case of figure A, they are constant, yeah. But in case of figure B, they are not constant. The characteristic directions along C plus and C minus are not constant, which is in case of subcritical flow. Whereas in case of supercritical flow, where the Froude number is greater than 1, only the upstream conditions would influence the flow characteristics at point P, the point where the flow, the characteristics directions meet. Only the upstream flow conditions would influence that. So this shaded region is called the domain of dependence or zone of dependence. And point P can influence points downstream. So the region in the, as you can see, this plot is x versus time. So for subsequent time, so we would influence the flow characteristics downstream. Yeah. But in case of subcritical flow, point P, in further time, it would influence the flow characteristics both upstream and downstream. So that area is zone of influence. So we need to differentiate zone of influence and zone of dependence. Here, what is labeled is the zone of the shaded area is the zone of dependence. Now, from known conditions at an alien point in time, then you should be able to determine the flow properties at their points of intersection from given states at points A and B. For example, here in figure 4.4, as you can see, there are the characteristics lines that propagates from point A to point P along the direction of C plus, and there is the characteristics direction that propagates from point B to point P along C minus, basically. Now, given the flow characteristics at point A, the velocity is given to be 1 meter per second, and the flow depth is 5 meters. And at point B, the flow characteristic, the velocity is 1.2 meters per second. And the flow depth is 4.8 meters at point B. considering Riemann invariance, we are required to determine the velocity and the water depth at point P. Now, assuming kinematic wave, in which case SF and S0 are equal, then we are talking about Riemann invariance. So we are going to calculate the Riemann invariance as V plus 2GH. It will be constant along the line C plus, or characteristic direction, or along the forward characteristics C plus. And V minus 2C, or V minus 2 radical GH, is constant along the backward characteristics, or C minus. So the values at A and the values at P along the forward characteristics, the Riemann invariance along that line is going to be constant. So we are going to calculate the Riemann invariant at point A, and then we are going to equate that with point P, the Riemann invariant at point P, which would mean VA plus 2 times radical of G times HA. That's the Riemann invariant at point A. Now let's calculate the Riemann invariant at point P, the corresponding Riemann invariant at point P along the C plus direction. So that's going to be the velocity at P plus twice of times radical G times HP. Since we know the values at A, we can substitute that, which is instead of V, A, we can put 1 meter per second. And instead of HA, we can put 5 meters. So that should give you a value of 50 meters per second for the Riemann invariant along the C plus, along the forward characteristics. And then let's find the Riemann invariant along the C minus, or the backward characteristics, using the values at B, which is the velocity at B is 1.2 minus 2 times radical G times the water depth at B, which is 4.8. Then this shall give you negative 12.52 along C minus. So we know the Riemann invariance already. Now we can calculate the values of V and H. Here in this case, the ones with our subscript here, or you can just put it if you like, VP and HP. Yeah, you can simultaneously solve this set of equations, and then you can obtain V is equal to 1.24 meters per second, and H is equal to 4.83 meters per second. I can just show you it here if you wish. So V plus 2C, the Riemann invariant. A is the point. AP is the line along the forward characteristics, and BP is the line along the backward characteristics. The depth is given at A 5, at B 4.8. Velocity 1 here, 1.2. You can easily calculate, given the depth, you can easily calculate the celerity. Square root of 9.81 times the depths. And then I just calculate similarly for B. Yeah. And then you can calculate the V plus 2C for A. For A is V plus 2C. But for B, since it's along the backward characteristics, it's going to be V minus 2C. So V plus 2C is, here is the V, plus 2 times that. That's the Riemann invariant along at JA. So this is basically JA. Yeah. This one is JB actually. Yeah. So this JA is the same as J plus. And JB is the same as J minus. So using this 15.02 something, So we can calculate the Riemann invariant at P, which is V1. Let me just say VP if you wish. VP plus 2CP is equal to 15.01. V2 minus 2C2 at point, using these are the values at point B. Here VP plus 2CP is equal to the values at point A, shall give you 15. Then VP minus 2CP shall give you VB minus 2CP. That's negative 12.52. If you simultaneously solve that, then that should give you the values of, which is actually, if you just add the two equations, then it is left with 2 times B is equal to 50 minus 12.52, then divided by 2, then that should give you the velocities at the intersection, basically. This plus this over 2. So that is 1.242. Once you find out the velocity at the intersection at P, then you can use either of these two equations to find CP. So that's basically here, it's the same as, no, sorry, that's basically here. Huh? So that would tell you V plus 2 theta here, 15 minus that one. Then minus the velocity here. Yeah, the velocity which we have obtained at V, which is 1.242. Then divided by 2. Then this should give you the value of the celerity at the intersection. So we have essentially found the velocity and the celerity at the intersection. Once you find the celerity, and celerity is equal to G times radical of G times the depth. So C squared over G shall give you the depth. So the depth of flow at the intersection shall be the celerity squared over G. So that's 4.829. So we have essentially obtained the flow velocity at the intersection and the depth at the intersection. You can also get the corresponding Q. As you can see it here, this is basically depth times velocity for a unit width. Shall give you the specific discharge here. And then here is going to be like that. And then the specific discharge at the intersection is like that. As you can clearly see here, between point A and B, the flow keeps on increasing along those 2 points. The flow is increasing, basically. Probably a gate, a sluice gate has been opened somewhere. So this would indicate somewhere at the intersection. And at a later point of time, the flow is progressively increasing. Now, we can expand this discussion in this manner. You can obtain the flow conditions like velocity and depth at a number of points. For example, consider a kinematic wave, in which case the bed slope and the friction slope are the same. And if you do have initial flow conditions, like velocity and depth, at a number of points, let's say in this figure, in figure 4.5, D1, D2, D3, D4, if you do have the flow characteristics like velocity and depth for the initial flow conditions, now you can easily determine the slope of the characteristic trajectories at each of those initial points. Basically, the slope is going to be like, for the forward characteristics, is going to be 1 over V plus C. For the backward characteristics, is going to be 1 over V minus C. Yeah. So we know essentially the velocities and the celerities. Yeah. Since we know the depth, so we know the celerity actually, which is radical of G times D. So we know the slopes. So we can graphically put from each one of those initial points, we can graphically put those characteristics directions. So those characteristics directions would meet at E1, E2, E3. Now and then we are able to determine, using the earlier example, we can easily determine the velocities and the celerities at E1. Using since we know the along D1 E1, yeah. So the values at E1 would be dependent on the values or the characteristics directions that comes from D1 and D2. D1 would go through the forward characteristics. D2 would go through backward characteristics. So using the values of the velocity at D1 and the depth at D1, which would give you the celerity at D1, so you can find V times D1 plus 2 times celerity at D1. Or essentially the Riemann invariant at D1 you can obtain. That's going to be the same as the Riemann invariant at E1 because they both lie along the forward characteristics. And the Riemann invariant at D2, which lies on the backward characteristics, is V D2 minus 2 times celerity at D2. And this would again pass through E1. So that should give you the Riemann invariant at E1, which is VE1 minus twice of CE1. Since we know the values are on the right-hand side, we can simultaneously solve this set of equations, and that should give you the velocity and the depth at E1. Now, similarly, you can find the values at E2, E3. Once you obtain the values at E1, E2, E3, then we know the characteristics trajectories or the characteristics directions. Graphically, you can put that if you wish. Yeah, and the point at where they join from E1 and E2, they will meet at F1. From E2 and E3, they will meet at F2. So similarly, you can determine the flow characteristics of velocity and depth at F1 and F2 using the forward characteristics and backward characteristics that starts from F1 and F2. Then ultimately you can obtain the flow characteristics at G1. Now, properties of the characteristics directions. Earlier we talked about, in case of still water, both the characteristic directions have the same magnitude. Of course, their signs are opposite, C plus and C minus, but they would have the same magnitude. This is the case for still water. Yeah, I remember here, for the case of still water, the wave, the disturbance, would traverse in both directions with the same magnitude, but opposite direction, of course. That's for still water. But the case for subcritical flow, since the velocity of flow is less than the celerity, there will be a component of the flow that would propagate upstream, basically. Of course, the one which is traversing downstream, since it's aided by the flow of water, the absolute wave velocity is C plus V, which is on the other side, what's moving on the other side is V minus C, which is smaller in magnitude and opposite in direction. So the magnitude is not the same. In case of critical flow, it would only propagate downstream. So the velocity of flow would have the same magnitude as the celerity. So the absolute wave velocity is going to be V plus C, since V and C are equal, it's going to be 2C. But in case of supercritical flow, it's totally also in the downstream direction, along the flow direction, and the absolute wave velocity is going to be C plus V. So, in case of critical flow, there is no backward characteristics line, it's going to be 0. In case of subcritical flow, there would be 2 characteristics lines of different magnitude and opposite direction. In case of still water, you're going to have the 2 characteristics directions of equal magnitude but opposite direction. But in case of supercritical flow, you would have the values of C plus and C minus will no longer be the same, and both of them, they would be in one direction. So in case of supercritical flow, information on the flow characteristics will not travel upstream here. So the state of the flow is only controlled by the upstream conditions, or the upstream conditions would influence the downstream conditions. But the downstream conditions cannot influence upstream conditions in case of subcritical, supercritical flow. Now, let's talk about the initial and boundary conditions. If you look at every one of them, you do have at a given initial point of time, the flow is t versus x. X is space and t is the timer. So at t is equal to 0, initial conditions we need to specify. But these 2 initial conditions would come in subcritical flow, in supercritical flow, and critical flow conditions from 2 different points. So determination of the initial condition requires 2 points, yeah, for the initial flow. But if you look at the boundary conditions, if you look at subcritical flow, we said GC plus the forward characteristics and the backward characteristics, they are opposite in direction. If you look at the upstream boundary condition, if you are interested to determine the flow characteristics on the left boundary condition, there would be C minus that's coming from inside of the computational domain, but C plus has to come from outside of the computational domain. So this has to be replaced by boundary condition. At least one boundary condition is formed upstream. If you look at the right side, or at point R, for the case of steel for subcritical flow, one characteristics would arrive still from inside the domain, which is C plus, but C minus has to come from outside to be able to determine the flow characteristics at R. So we need to have one characteristics from inside and one characteristics from outside. And this has to be replaced by boundary condition, downstream boundary condition. So for subcritical flow, we need to have one boundary condition in the upstream and one boundary condition in the downstream. Conditions are required. These boundary conditions for supercritical flow are different in number. In case of supercritical flow, remember, both C plus and C minus are of the same direction. So at the boundaries, let's say on the left boundary condition, on the left boundaries, like on point L, To determine the flow characteristics at L, we need to have those two characteristics, both of which shall come from upstream. So we need to replace these by two boundary conditions to specify the conditions at L. To specify the conditions at R, both of those characteristics have to come from inside the computational domain. So you don't need to specify the downstream boundary condition for supercritical flow. So supercritical flow requires two boundary conditions only on the upstream side. They don't need boundary conditions on the downstream side because they are not influenced by downstream conditions. In case of critical flow, one boundary condition, it's vertical, it's known already. So you need to specify one boundary condition. It's almost similar with the subcritical flow conditions, except that it doesn't need to have a downstream boundary condition as such. But the case for, like I said, the case for supercritical flow is completely upstream controlled. So you only need to specify two upstream boundary conditions. But the initial flow conditions require 2 points. In each one of them, it needs 2 points. In subcritical flow, in supercritical flow, or in critical flow, you need to specify 2 points. Now, let's look at another example. Consider a long channel flow measurements at two gauging stations given at t is equal to 0. Their locations is given. One is at downstream at 7.1 kilometers. The other one is at, one is at upstream at 7.1. Station 2 is at downstream, 8.25 kilometers. The water depth at station 1 is 2.2 meters, whereas at station 2 it's 2.45. And the flow velocity at station 1 is positive 0.35 meters per second. At station 2 it's positive 0.29. Assume kinematic wave. You are asked to plot the characteristics issuing from each one of the gauging station in the xt plane, assuming straight lines. Calculate the location, the time, and flow properties. Basically, the velocity and the depth issuing from the two gauging stations. Now, for a kinematic wave problem, it's not equal to SF. So those 4 systems of characteristic equations would apply. Riemann invariance. So total derivatives of V plus 2C. So V plus 2C is constant and V minus 2C is constant. V plus 2C is constant along the characteristic trajectories of V plus C. And V minus 2C is constant along the backward characteristics of C minus. Now, we can calculate at the intersection of the forward characteristics issuing from station 1 with the backward characteristic issuing from station 2. So the trajectory equations would satisfy from change in x per change in t is equal to V plus C. You can obtain from here, let's say if you try to find out along forward characteristics, this would mean x, change in x per change in t is equal to v1 plus c1. v1 is the velocity at station 1. c1 is the celerity at station 1. The celerity at station 1 is computed as radical of g times depth at station 1, which is 2.2. So using that, you can find the celerity to be 4.6456 meters per second. And the celerity at station 2, it's using a depth of 2.45, shall give you 4.9 or 25. Now, the characteristics directions, straight line, is x equal to x1. x1 is the location of station 1 plus velocity 1 plus celerity 1 at station 1 times change in time, starting from a time of 0 to t. Yeah? So you can just place instead of x1 in terms of meters, which is 7.1, in terms of meters is 7,100 meters, plus the celerity C1, which you have found 4.9956. Oh. That one is not correct. So we need to calculate that. So this shall give you here 4.9956. Huh? Oh, it should be 4.9956. So the celerity is essentially, it is calculated here. Huh? So here the locations are given: 7.1, 8.25, depths 2.2, 2.45. Then you can find the velocity is given to be 0.35 and 0.29 here. So first, let's find the celerities here. So the celerity is given here as 4 square root of this times the depths. Yeah, that's the celerity here. And the celerity is 4.902. Yeah. So this is the velocity plus, that's the velocity plus the celerity. Yeah. So the velocity plus the celerity. So obviously it's this one plus that is 4.9956. Yeah. So this term is 4.9956. And then this one is for station number 1. Huh? For station number 1. For station number 2, x is equal to x2, which is 8.25 kilometers, which is 8,250 meters, minus v2, which given us 0.29, minus the celerity, 4.9 here, or something, shall give you 4.6125 t. So let's simultaneously solve this set of equations here. Yeah, so if you try to solve this set of equations here, you can clearly obtain, if you just deduct the two equations, yeah, you can easily find here and then easily find the value of t from here. Huh? So if you just easily deduct the two, that's the difference between the two, and then negative sign here, and then the difference between the two here. Going to be positive 9.6 here, and then you just divide that. Then that should give you here the time. Once you find the time, let's plug it here in any one of the two equations. Then that should give you the value of the x here. Yeah, using this time and using the first equation here. So x is 7.698 kilometers. So the point at which those characteristics directions meet would be at a location of 7.6, 7.7 you can say roughly, or 698 you can say if you want to be too precise. Yeah, basically that's the location, and this is the time, 120 seconds roughly. Similarly, the Riemann invariants are going to be calculated as v plus 2c is equal to v1, the velocity at station 1, plus 2 times the celerity at station 1 is equal to 9.641. v minus 2c, the v and the c, the velocity and the celerity at the intersection point. That's for the forward characteristics, and this one is for the backward characteristics. The second equation is for the backward characteristics. The first equation is for the forward characteristics. So using station number 2, you can obtain negative 9.515, and then you can simultaneously solve these two set of equations now. So you can obtain, if you just add the two equations if you wish, then divide it by 2, then that should give you the value of the velocity here. Add the 2 and then divide it by 2 as the velocity. Once you obtain the velocity, plug it here, and then deduct 9.641 times the velocity which you have obtained and divide it by 2. Yeah, so this value minus the velocity which you have obtained and divided by 2 shall give you the celerity. So we have obtained now the celerity. So we have obtained already the velocity to be 0.06, the celerity to be 4.789, and then you can obtain the depths, because celerity is equal to square root of g times d. So c squared divided by g shall give you the depths. So the celerity squared divided by acceleration due to gravity shall give us the flow depths. So the flow depth is going to be at the intersection point 2.338. If you obtain then the flow depths, then you can easily obtain the specific discharge. Initially it was 0.77. Then at station number 2 is going to be 0.711, it's decreasing slowly. And then at the intersection, it has tremendously reduced. It looks like there is a sudden shutdown of a gate somewhere. And this would be noticed after about 120 seconds at a distance of 7.7 kilometers, it looks like. So at a distance of 7.7 kilometers, after a time of 120 seconds, the velocity is going to be 0.063, which was initially 0.35, at station number 2, 0.29. Now it has tremendously reduced to 0.063. Celerity is 4.789. Depth of flow is 2.34. And the specific discharge has reduced to 0.414 meters square per second. Against specific discharge of 0.77 at station 1 and 0.71 at station 2 at times equal to 0. So it looks like there is a reduction in flow rate. Probably there is the gate has been closed. Now, as you can see, we can determine, this is the case for subcritical flow, as you can see. We can determine the flow characteristics from both upstream and downstream points, and then determine the flow characteristics somewhere in between. So that would influence because the effect of certain process somewhere from upstream and downstream can be felt somewhere in between. So we are able to calculate now the flow characteristics, the location, and the time. Now we can employ this analysis for detailed analysis for a number of points in a given cross section of a stream. Now, participants, you are required to do these problems. Of course, you would have an assignment which would either refer to these equations plus some more additional on method of characteristics. So, next class, we'll talk about finite difference method. Thank you for now.